Good afternoon everyone, I'm Mr. Ish. Let's look at this video over here. Trigonometric integrals can get complicated, and that is something we will see. I'm going to do in this video a natural progression of 4 integrals, trigonometric functions, and we'll see how each builds on the other in terms of complexity. As a general observation of mine, the integrals which involve secants and which involve tangents tend to be more complex. And when I'm saying secant and tangents, I would also include cosecants and cotangents. These generally tend to be more complex than those which involve sine and cosine. That's just how it is. And when we start adding powers on top of these, like secant square x or secant to the 4th x, or even like tangent to the 7x, when we start seeing these type of functions arise, then the integrals can get quite complex unless we can start finding patterns or shortcuts. And in this video, when I go over the 4 examples, we'll see how each progresses in terms of complexity. It's just a survey only. You could essentially get lost in doing these trigonometric integrals, and then you would be thinking in your head, like, when does it end? It basically ends whenever you decide when it ends in terms of the complexity of integrals that you want to learn. Always with everything when it comes to math, you start from the basics. Once you learn the basics, you can challenge yourself with something more complex. So let's proceed with this video. So I'm hoping from these 4 examples that I'll present accidentally or incidentally, none of these are already presented in a previous video. Hopefully they're not, but let's start with this one. We have the integral here to find for tangent cube x. It can be a rather messy question unless you're able to determine or decipher some form of a pattern. The best thing you can do over here is split this into this form, tan x and then tan square x dx. Your goal is somewhat to eliminate something to make it easier and more manageable. And you have to think about trigonometric identities. Tan square x plus 1 is equal to secant square x. And we can proceed with that. We substitute tan square x for secant square x minus 1. And then we have a dx. Remember, the Pythagorean identity is tan square x plus 1 is equal to secant square x. Therefore, tan square x must be secant square x minus 1. Open this up and redistribute everything across its own integral sign. We'll have tan x secant square x dx, and then we have this minus redistributing across the minus sign, minus integral tan x dx. Remember, we're going from easy to hard. So this question is easy, the next one will be slightly harder, and then onwards. Here you do basic polynomial substitution, but using trigonometric functions. U is equal to tan x, du is equal to secant square x dx, and dx is equal to du over secant square x. And all of these are indirect integrations. We're not doing direct integrations, they're indirect, so that's fine. Here we substitute u for tan x, then we have secant square x, then we have du over secant square x, then minus integral of tan x, which is easy. Here we can complete it. We'll have integral of u du. Integral of u is just u square over 2. Integral of tan x is minus natural log secant x, and then plus c. All you have to do here is substitute back for u, and we'll put the final answer right over here. It will be tan square x over 2 minus natural log secant x, and then we can just put a constant of integration, and this question will be completed. But you can see it's rather tricky, but not overly complex. The trickiness only arises from the fact that you're dealing here with a Q function, and you should separate it out so you can bring a trigonometric identity and then proceed from there. Let's go to the next question. Now this is question number 2, and we have secant cube x. Secants are always more difficult than tangents. They just are. And that's my observation, but I believe my observation is true to a certain degree. Just secants tend to be a little more tricky. Remember, you have multiple techniques to incorporate or utilize. Incorporation of a technique or the implementation of a technique depends pretty much on how experienced you are with integrals, and experience only comes with practicing and of course failing, right? When you fail, you learn. When you learn and you practice and you keep doing that, you end up getting that experience. The technique to utilize over here is integrating by parts, and the only way you can best realize that if you separate this out. And by separating it out, I'm talking about this. We're looking at secant x secant square x dx. U is equal to, what are we going to use for u? Remember, we're using integrating by parts. uv minus integral of v du is going to be integral of what? U dv. This is what we're aiming to utilize over here. Therefore, we must do some smart substitutions. If u is equal to, I'll use secant x, because these are the only items I have available and these are the only items I can use. If u is equal to secant x, du must equal to secant x tan x dx, right? The derivative of secant x is what I've shown you over here. V must be equal to the derivative of that which remains, which is secant square x dx. And you know there's a library of good antiderivatives, one of which is this. Anytime you see this, you're thinking what? You're thinking tan x. Why are you thinking that? Because if you do the derivative of this antiderivative, you'll go back to the original function, which is secant square x, right? If you do the derivative of this, tan x, you get secant square x. Therefore, the antiderivative or the integral of secant square x must be tan x. So now we have everything we need to proceed over here. uv minus integral v du. U was what? Secant x. What's v? Tan x, right? Minus integral of v, tan x, right? V is tan x. What's du? Du is all of this. Secant x tan x dx. In the next step, open up these things. I'll just write secant x tan x is my first item coming from here. Integral, I'm combining the two tangents together. I'm getting tan square x secant x dx. Now, if you understand or realize that we can do a substitution over here. Tan square x, based on that identity, is equal to secant square x minus 1, right? Tan square x plus 1 is equal to secant square x. Therefore, tan square x must equal to secant square x minus 1. Remember this right here, this question is slightly more complex than the one you've seen before. It's more complex because we're dealing here with secants versus tangents. You have to substitute this right into this. You get secant x tan x minus, let's substitute this over here, secant square x minus 1 times the secant x, which you're seeing over here, dx. In the next step, let's combine, or let's open that. I'm getting what over here? I'm going to get a distributive product over here, right? We'll distribute it. We'll get secant cube x minus secant x dx. We should separate this out across its own integral sign over the minus sign. And I have to generate some space for that, right? Let's come over here. We're going to resubstitute we're going to redistribute across the minus sign. And remember, all of this right here so far is equal to this, because this right here, this entire procedure is stemming from the question we have. Let's do the distribution over here. We're coming from here all the way up to right here. We have secant x tan x. Remember, you have to write everything as you see it for those steps which are not being manipulated. Secant x tan x minus, well, let's separate this and distribute it across the integral and the minus sign. I'll have a minus secant cube x dx. This minus and this minus will become a positive, right? Positive secant x dx. All of this is equal to, let's put an asterisk, all of this is equal to this, what you see over here. And you know there's a familiar shortcut we know. We can take this portion right here, because it's similar to just that. We can take it across that equal sign and add it over here, such that you'll have secant x tan x plus this integral of secant x dx is equal to, remember, I'm taking this component right here on the other side and I'm adding it to this, because all of this resulting expressions is equal to that, is equal to 2 integral secant cube x. And you've seen this technique before. Since our original question is what is the integral of this, we're actually just solving for that. We'll take the 2 on the other side and we'll divide everything here by 2 after I've done the integration of secant x, which we know what it is. Let's finish this here in this last step. Secant x tan x plus integral of secant x is natural log secant x plus tan x. I'm putting in absolute values because you don't want to do natural logs of negatives. You do natural logs of positives all over. This 2 comes on the other side, you divide it, plus c. So you could have said 1 over 2 multiplied by this sum, or you can do this sum right here on the top and divide it by 2 under a unifying denominator, and it's just as good. And here's your final answer. So you can see this question was slightly more difficult. It was more difficult because we start here with integrating by parts, but using functions which are relatively not too easy, because we're dealing here with secant x. Secant x, when you find the derivative, expands into secant x tan x, then you run it through, and then down over here we end up seeing this part pop up right over here, which looks very familiar to what we're trying to decipher from the beginning, but you marry it to your original question, and you come down over here and you take it to completion. And you have the benefit of looking at this at a slower pace because you have the question here solved out for you, and you can study it and just see how it was done. So we have 2 more questions to review, including this one. We have 1 more. And keeping in mind and the theme of today's video is each question is more complex than the one previous. And here we have tan to the 6th and we have secant to the 4th. In terms of powers, these are higher powers, therefore the question is more difficult. Question is also more difficult because we have secants involved over here. Our goal always is to use our experience and our techniques to make the question more manageable, and I can do so by recognizing this. I have tan to the 6th, then I have secant square x and secant square x dx. I've separated the secant to the 4th, separate secant square x's. By doing that, I've made the question more manageable, and this is how it's going to play out for you. Use your trigonometric identity. Tan square x plus 1 is equal to secant square x. You have tan to the 6x. I'm substituting 1 secant square x for 1 plus tan square x secant square x dx. I'm not doing both because you'll see shortly there will be no need for you to eliminate both. But you see how we've gotten rid of one secant function and we brought in another tangent. And I like tangents over secants. They're easier for me to mentally grasp and handle. I can do a substitution over here. If u is equal to tan x, just do u is equal to tan x, then du is equal to secant square x dx. And polynomial substitution technique, dx is equal to du over secant square x. We just bring in the u's over here. U to the 6th, parentheses 1 plus u square, secant square x, and then du over secant square x. These are just cancelled out by looking at this and employing it into our question. What we essentially just have is u to the 6 times 1 plus u square du. Technically more difficult of a question, but in terms of utilizing experience and technique, it actually becomes easier than the previous question we've just seen. You just have to open up the parentheses over here, u to the 6 plus u to the 8 du. Integrate this, it's easy. It's basically just simple polynomial integration. U to the 7 over 7 plus u to the 9 over 9 plus c. I won't bring in the plus c yet because I'll finish it over here. U was originally tan x, therefore it's tan to the 7x over 7 plus tan to the 9x over 9 plus c, and this here will represent your final antiderivative of this integrand over here. Now I cannot tell you for sure if these are true functions or they're realistic, whether they're realistic functions, but they're good exercising questions. So here is our last question. We have the integral to find for tan to the 5x and secant to the 7x dx, a product of these two functions, and they have powers, as you can see, of 5 and 7. I have the previous question written over there, tan to the 6x and secant to the 4x, only just to make a specific observation or a point. You see in the previous question we had powers which happen to be even numbers, 6 and 4. Here the powers, the exponential powers, are 5 and 7, they're odd. It is my experience alone. Generally, even integrals are easier than odd integrals. Whenever, if and all possible, try to convert your odd powers into even powers, and you can do so by some sort of trigonometric identity or substitution. If I were to somehow pluck out a tan and a secant x from here separately, I could rewrite my integral as a secant to the 4x secant to the 6x. I've plucked out a secant and I've plucked out a tangent from this original question, and I'm writing them separately. Secant x tan x dx. If you were to open this, you would end up exactly here. I've not done anything other than just manipulation, and this is very legitimate, valid manipulation we can do. I've plucked this out and I've brought the powers into more manageable forms. I can do another thing over here to make the question even more manageable. I can think of this in terms of the trigonometric identity. Remember, the identity is tan square x plus 1 is equal to secant square. I'm using abbreviations. Therefore, tan square x is equal to secant square x minus 1, right? I can view the tan component in this form right over here. So let's do it. When we view it in this form, we're really looking at secant square x minus 1 all square, because that's going to generate you this. Remember, tan square x was equal to secant square x minus 1, but we have tan to the 4x, so there must be square of that. It must be square of that. And then we still have secant to the 6x, and we still have all of this afterwards. But all of this afterwards does not by any means make things more complex. And you'll see it'll make everything easy for you too. Now all we have to do is just substitution. If u is equal to something, we'll come up with a good substitution. Let's do the substitution over here. If u is equal to secant x, then du must equal to secant x tan x dx, and then you know polynomial substitution, dx is equal to, you take that derivative on the other side, you get du over secant x tan x. All you gotta do is employ this. U was equal to secant x, so where we have secant x, let's put in a u, but here I have secant square x, therefore it must be u square. Right? Secant x is equal to u, secant square x must be u square. Then I still have this u square minus 1 and then whole square. Here I have u to the 6 because secant x is a u. Secant to the 6x must be u to the 6x. I'm not resubstituting anything over here because this is going to cancel out, as you will see. Du over secant x tan x. This cancels out. So essentially what I'm left with is u square minus 1 whole square times u to the 6 du. All I have to do is open this up, multiplied by u to the 6, and I'll have a polynomial expression over here, which will be very easy to integrate. So the complexity of these type of questions, which make them hard, is to recognize patterns, recognize techniques that can somehow convert this initial difficult expression into something which looks something of this sort. U square minus 1 whole square is really u to the 4th minus 2u square plus 1. When you're multiplying it by u to the 6 du, it's easy. You're going to end up looking for the integral of u to the 10th, because now I'm going to open up the parentheses. Everything's going to multiply with this u to the 6 as you open it up and you distribute it across. U to the 10th minus 2u to the 8th plus u to the 6 du. The integral of this, or the antiderivative of this, is easy. It's u to the 11 over 11 minus 2u to the 9 over 9 plus u to the 7 over 7 plus c. In the last step, let's substitute. U, as you know very clearly, is this secant x. So I'm having secant to the power of 11 x over 11 minus 2 over 9. See, 2 over 9 times secant to the power of 9x. See, 9x. Plus, you can just say 1 over 7, or you can do secant to the 7 over 7, and we have secant to the power of 7x plus c, and that right there will represent our good final answer. So you have 1 over 11 secant to the power of 11x minus 2 over 9 secant to the power of 9x plus 1 over 7 secant to the power of 7x plus c, and that completes this question. So this right here is our final answer, and it's good. Difficult question and not your typical or your normal question that you will see, but your experience and your comfortable, or let's say your experience and your comfort with these type of questions must extend to the level of these sorts. And there are many more of these type of questions that we can look at. It just basically depends on where we draw the line. It basically depends on anyone's personal initiative and motivation as to how far they want to go. Learn and start with the basics, then challenge yourself with something more difficult. And that'll be it for this video. I hope you enjoyed this video and it proves to be materially beneficial to you all. Thank you for watching. Have a nice day.